So when people talk about equivalency and equivalent, there's a couple of things that they don't often bring up. I'm not saying there aren't solutions, but they don't bring them up, and I'd just like to talk about a few of them. So here's one example. They say that there's a person standing on a planet like the Earth. What he feels as gravity, they say, is equivalent to if a person were in a rocket ship that was under uniform 1g 9.8 meters per second squared acceleration. And they would be equivalent, indistinguishable from each other. That's the claim. So one of the things I wanted to point out that's different between these two is conservation of energy and conservation of momentum. A person standing on the Earth, his kinetic energy is not increasing. His momentum is not increasing. That's just static. The person in the rocket ship, and for the moment, we're not going to look at how the rocket ship is achieving its acceleration of the person. In the wider universe there, yes, there's conservation of energy and momentum. But the person themselves in the rocket ship, that person's kinetic energy is increasing. Their momentum is changing of that person. So there is a difference between those two states. One in which it's accelerating, increasing kinetic energy and momentum, and changing momentum, and the other one where it's not. Another one is where we have someone who's in free fall and someone who's constant velocity in a spaceship. Now, the free fall is like, say, in a vacuum where you don't have wind resistance and so forth. And people will often, again, say these are equivalent. They're equal states. They're the same, blah, blah, blah. And again, you can say they're equivalent in a lot of ways, very similar to each other. But from a conservation of energy and momentum point of view, they are different things. The person who is in free fall, and again, it doesn't really matter so much how he's accelerating. It's just that his velocity is changing. So his kinetic energy is changing. And so that's very different from the person who's at constant velocity. He might be oblivious to it, but his kinetic energy is increasing. It's a difference between the two things. And then here's another one where they say it is equivalent. Say on the left-hand side, say a person is going at a high speed or accelerated toward that cement asphalt, and when their face hits it, a stationary object like that. Or on the far right, if the stationary object, if the cement sidewalk was the thing that was moving and smacked the person who was stationary, it seems the same either way. Or if you were somewhere like in the middle, you're in a mix where maybe half speed, to each, or 90-10 or whatever, that it seems that it's the same. And I would agree, in a lot of ways, it will seem like it's the same. But from a conservation of momentum, conservation of energy point of view, there are differences. What it would take for a stationary object like the Earth to sit there and to accelerate a person, to spend the energy to move him and accelerate him at a certain speed and a certain acceleration into that cement sidewalk is one thing. It takes an entirely different scale and magnitude of energy to have that person be stationary and take a giant object like the size of the Earth and say, I'm going to accelerate the whole planet into this person, but I want that person to stand still. So I can smack them by moving the planet instead of moving them. There is a huge difference between those two in a momentum and energy point of view. Now, from the person's point of view, his face just hit the cement. He might not be able to see a difference. He might be oblivious to the difference, but there is a difference in that context. So that's your conservation of energy, conservation of momentum. And the other way is to look at this separate from those two is curvature of spacetime. So in relativity, what we attribute to gravity is the curvature of spacetime, which is a result of an object's energy density per unit volume. So the reason you have a black hole or a star is because the amount of energy, it could be mass, like rocks, liquid, gas, or it could just be energy, kinetic energy, sound energy, light energy. So, for example, you can look up equivalence, where you can create something with as much gravitational curvature as a black hole just by having a bunch of light, a bunch of energy, all focused on the same small region of space. You can curve space just with that energy. So because of that, in this thought, where you have a person standing on a big planet, his kinetic energy is not increasing. The curvature of that system is not increasing, of him is not increasing. But the same person, if he were being accelerated in a rocket ship at the same 1g rate, his kinetic energy is increasing. So eventually, his curvature created by his increasing kinetic energy also begins to increase. And if he has enough kinetic energy, he forms a black hole because he has enough energy to curve space that much. And if you didn't want to go to the scale of a rocket ship, where the person's kinetic energy was large enough to do that, you could, in theory, be able to do this in a lab where you have an acceleration out of a railgun or a particle collider, and you could say, so that object's accelerating, or that object, weighs 2 billion pounds. Do they both cause an equal curvature, an equal gravitational attraction, because it's accelerating, or because it has this much, energy content, like from the mass? And you could run that experiment. And you could also say the energy of the kinetic energy compared to the rest mass energy, and you could run that experiment. I'm not aware of anybody actually running those experiments per se, to see that the wall has a gravitational pull on you because you have a particle collider there, or you have a railgun or something. But in theory, you could do that, as the curvature would be another difference between, or a potential difference. So that if they were perfectly identical, then you create a situation where there's a problem because the accelerating object has increasing kinetic energy, which means that should be having increasing curvature. With a person just standing on the surface of the Earth, his kinetic energy is not increasing, his curvature is not increasing. So there's a difference there. Whether he's oblivious to it or not, there's a difference.